Okay, welcome to the second part of the video series on equilibrium balance and levers. In this particular scenario, we've got the humerus, the upper arm bone, the ulnar radius, of your forearm, and we've got this bicep muscle attached to the radius, right? In this scenario, again, we're trying to find the static equilibrium condition to hold the forearm and hand in this kind of a position. Remember, this whole system would rotate, in this case, around the elbow joint, right? The center of mass of the ulnar and radius is a specific distance from this axis of rotation. Again, your books would be able to tell you exactly where it is as a percentage of the length. I'm just drawing this here to take you guys through the way of calculating. But since this is a given distance from this axis of rotation, if the muscle was doing nothing, we would get a net rotation in a anti-clockwise direction. Right, so it's kind of the job of the bicep muscle to kind of prevent that from happening and maintain this static equilibrium condition. Right. In this case, the weight of the forearm and hand is a mere 2.3% of total body weight. And in this case, the body mass is 70 kilograms. So you can use this information to get the approximate weight of the forearm and hand. Again, it's important to note that the center of mass of the forearm and hand is a certain distance from this axis of rotation. And in this particular scenario, I've given it as approximately 28 centimeters, right? Now, the goal is for the muscle to prevent that from happening. And again, I'll just draw the vertical component of this muscle, the vertical force that the muscle will be producing, which we'll call Fm. And that is also a certain distance from the axis of rotation. Similar to the previous example, I've given this to be 5 centimeters. So remember, as always, when you're dealing with forces and the distance that forces are from an axis of rotation, the units for distance must always be in meters. Alright, so I think that's pretty much all the information that you need to solve the problem. The question is, what is the problem that you're trying to solve? On the one side, it's the muscle force, and on the other side, it's the mechanical advantage of the system, right? So first of all, we have to kind of unpack what kind of a lever this is. So if we have a scenario where the fulcrum is on the one side and the force and resistance arms are both on the opposite sides, both on the same side of the fulcrum, then you're going to be either dealing with a second or third class type lever. In the case where the force arm is closer to the axis of rotation, and the resistance arm is further away, you're dealing with a third class lever, right? Most of the joints in the human body are based on this kind of a lever system. Alright, so let's get to unpacking this, right? So again, let's get a convention going in terms of anything going up and to the right is given a positive value, and then anything going in an anti-clockwise direction is given a positive value. And sorry, I think earlier here I stated that this was anti-clockwise, but it's obviously clearly clockwise. Sometimes my thoughts get ahead of me. Alright, so clearly the center of mass of the forearm and hand is giving a clockwise rotation about this axis of rotation. So remember to solve any kind of torque. Example for static equilibrium, the sum of all the torques acting on the system have to equal 0. So the sum of all anti-clockwise moments must equal the sum of all the clockwise moments. Right, so if I start unpacking the clockwise side of things first this time, so I'm trying to solve for this part because that's what my center of mass is doing. I have to find, and I'll call this the force, the weight force, which in this case is the weight of forearm and hand, excuse me, which is 0.023 times body weight, which will be 70 times 9.81. right? So all of that is the FW component, and that has to be multiplied by the distance that it is from the axis of rotation, which is 28 centimeters, which I have to convert to meters. So that's 28 centimeters multiplied by 1 meter per 100 centimeters, right? Which will give me 0.28. So this over here is, I'll refer to that as D2. Alright, so all of that, if F1 FW times D2 is all of this, that should equate to the following, and I'm just going to double check my values. That's going to equal 4.42 Newton meters. Alright, on the other side, I've got the muscle force. So this is the anti-clockwise moments. Remember, if this muscle force is pulling upwards, it would cause the system to rotate this way around, which is anti-clockwise, right? It's the muscle force times, and I'll call this D1, that's 5 centimeters is D1, multiplied by D1, which is, like I said, 5 centimeters, multiplied by 1 over 100. Just put the units in there, and that's obviously centimeters. And therefore I have 0.05 Fm is equal to 4.42 Newton meters. So therefore Fm is 4.42 divided by 0.05, and remember that's Newton meters divided by meters, and that's going to be equal to 88.4 newtons. Right? Question that still remains, since I've now solved for that, is what's the mechanical advantage of the system? So remember, mechanical advantage is equal to the force moment arm divided by the length of the resistance moment arm. And it should be clear from the previous example that the resistance moment arm is much greater than the force moment arm, and therefore will most likely sit with a mechanical advantage in favor of the force again. So here force moment arm is 0.05. If I divide that by the 0.28 of the resistance moment arm, I'm going to sit with 0.18, which is clearly much less than 1. So again, this favors the resistance. And again, we can see that the weight of the forearm and hand is, what did I say that equates? So all of this basically equates to 15.79 newtons. So that's the weight of the forearm and hand. And you can see here I had to produce a significantly greater amount of force to counteract that. And part of the reason is because my force arm is so much closer to the axis of rotation, whereas the weight, the center of mass is so much greater, right? So against that ratio of these distances that dictates that. So again, not favorable for the amount of muscle force that I have to produce, and again, that's the trade-off, right? The arm muscles aren't designed for force production, they're more designed for speed, right? So again, if you kind of think about it this way, for just a small movement of the muscle, if this shifts this, if kind of like bar, if you want to think about it that way, it only moves a small distance over here, but the further away we go, the distance that resistance component moves is much greater, right? So I get much greater speed because I'm covering a given distance or greater distance in the same amount of time that the part that's closer to the axis of rotation moves, right? So arm speed can be much greater with a small force, right? But again, the trade-off is that it's not designed for strength, more designed for speed. Anyways, I hope that part makes sense. I'll see you guys in the next video.